Welcome. Thank you for tuning in to today's discussion. For today, we will look at diagramming and modeling communication between computers within a single local area network within a single subnet. And we'll look at what happens behind the scenes when we build a frame that needs to be sent out. And we'll also look at what happens if we don't have all the information to build that frame correctly. And namely, if we don't have a destination MAC address, what we would have to do in that case to find that particular destination MAC address out. And obviously the mechanism we'll use and look at today is address resolution protocol. The second type of communication we'll look at today would be communicating from one computer in a single subnet to another computer in a second or different subnet. So a subnet that happens to be external to the one that the originating computer is actually a part of. To begin, let's open up the diagram information that we're going to build within Packet Tracer. For this particular demonstration, we'll be using two different subnets. I've labeled them Subnet A and Subnet B to help you with differentiation or basically being able to distinguish one from the other. However, in reality, we want to distinguish them by their numerical values, by their dotted decimal notation values. So subnet A is the subnet 192.168.1.0. We're using a /24 mask. That is what we would call a default subnet mask for a Class C address. And then the second subnet, 192.168.2.0/24, we can see the third octet value is different. In subnet A, it's .1.0, and in subnet B, it's .2.0. I've also listed the default gateway router interface information. In both cases, we are following best practice, and that would be to use the first assignable or usable address in the given subnet for the default gateway router interface, for that particular router's interface that will serve as a default gateway. We've done the same thing again in subnet B. We're using the address 192.168.2.1. Again, that's the first usable address. Remember, if we were to start with .0 with the subnet A 192.168.1.0, the problem is that's a reserved address. It is the subnet ID, something we'd call the network ID, or subnet number, network number. Same thing also would be true for subnet B. We can't use .2.0. That is reserved. Additionally, I've also listed PC information. We're going to have two PCs in the first subnet, subnet A, and we'll have another PC in subnet B. With that being said, you can certainly pause and write this down or make sure you've made note of these values. We're going to use these values to build our network, and then we're going to look at how communication works in a single subnet, in a single LAN, and how specifically ARP operates in order to help communication work. And then again, secondly, we'll look at what it would be like to send a ping message from PC 0 to PC 2, which happens to be in an entirely different subnet. Right, if you can open up Packet Tracer on your end, that would be wonderful. As I build this, remember, you can always pause as you're viewing in order to help you understand what's going on and be able to keep up with what's happening. For the moment, I'm going to build this after snapping this particular window to the side. The reason being, I'm going to open this one as well and snap it to the left. But once we get the whole thing built, I'm going to actually close the notepad diagram. So, with that being said, let me clean that up. All right, we're going to use an 1841 router. So you can simply click on it, left click, and drag the router to the top of your canvas. On top of that, we're going to go down to the switch icon, the switch object, and we're going to also grab a switch, which is a 2950 switch. I'm going to grab two of those because, again, we're going to be building two different subnets, two separate local area networks. All right. down to the computers, if I hover over the end devices, you'll see that's there. If I just click on it and drag it out, you'll be able to see what's going on. Now I could single left click the object down here and see my choices, but for our purpose, we're going to kind of take the abbreviated approach and just drag these stock devices out to our canvas. This is our working platform where we're going to simulate to help you better see what happens as network theory meets network practice. The same thing will be true for cabling. I'm going to click on, make sure I click on there, sorry. Click on the lightning bolt that's orange and yellow, and I'm going to just use this first option. Now, I'm hovering over it, you can't read all the words, but this allows you to automatically connect one device to another. In reality, as you continue to move further along into networking, you'll want to know the exact cables, you'll want to know which interfaces to use, you'll want to be able to set all this up manually. For right now, we're just going to left click on that, and we're going to then single click on the PC 0, single click on switch 0. We're going to do that one at a time. So the program itself is determining which cables would be best to use to connect all these devices. And by best, I mean correct. So I'll continue to do that. Left click, and click on the switch. And again, left click, once on the switch, once on the router. The other thing I like to do, a couple things, would be click fast forward time. So, if you build networks or diagrams within Packet Tracer, different schematics, once you've set it up, you can click fast forward time, and behind the scenes, since this is a simulation software, it will boot up the different devices, in this case the switches and the routers, immediately so that they're ready to go. We could actually connect into the router and start typing commands. Now, the other thing I want to point out to you, if you click Options up here, you may not know this, and then Preferences, there are two different checkboxes that you could potentially select. I always like to click this particular checkbox where it says Always Show Port Labels. The reason being, in IT, it's very important to know which interfaces we have to configure, and it's nice to see that visual representation. I don't always show the device names themselves, the labels for those. So at some point during this, I might turn that off. But for now, at least you can see here's router 0. See if I can give a little extra space. Here's switch 0. You can kind of see it within there. It's a little bit muddled. But again, for now, for our intent and purposes, we're just going to leave it as such. All right, what I'd like to do next with you is to configure all of the different PCs. Now, if you haven't recognized, we have a router. A router is used to separate one subnet from another. And so in this case, you can see there are two different interfaces, FA00, FA01. So on the left, we will have our subnet A, and we'll have to fill in the computer information and also that router interface information. So here's the subnet over here. And on the right, we have another subnet, which is subnet B, 192.168.2.0, and we'll also fill in that PC information for PC2. It's just helpful to recognize that when you look at diagrams and you see routers there, we want to immediately discern and understand, okay, they're separating traffic, and specifically, they're separating traffic from different subnets. All right, let's continue. In order to configure a PC, we'll left-click on the object itself, and then click on Desktop and IP Configuration. And once you've done this for one, you'll want to repeat the process for the other two. I'll continue to do that, but you'll become more adept at doing this. PC 0 is supposed to be .11. I'll click Tab, and then in clicking Tab again, I'll move down to that final field that we will want to fill in. Now, there is another field for DNS server as well as IPv6. Those certainly could be used for later model demonstrations or builds. For our purpose, though, we don't need to do that. So with that being said, let me actually highlight this. I'm going to copy, because we're going to use it in a little bit. Let me show you that we do have the first PC. It does match this right here. My mask, it automatically populated that for me. It recognized it was class C, and so it just gave it the default subnet mask. Let me click X. You do not need to save. Once you enter the information in the fields, if you close it, that information will be saved. One way to check or verify that would be to hover over the PC, and we can see that the link is up, the IP address is set with the proper mask, and in the far right column there is a MAC address, something we'll want to know at some point. The gateway also is set to 192.168.1.1. So let's continue with the next PC. Click on PC 1, click on desktop, click on IP configuration. I'm going to paste now. I did intentionally copy that portion, those first 3 octets of the IP address from the last computer, just to save myself time. That's something you'll want to think about. How can you work efficiently and accurately so you don't make mistakes? And so now I've done that. I'll double check my work. PC1, which is what we're in right now, is IP address 192.168.1.21 with the proper mask /24, which is 255.255.255.0, and then the default gateway 192.168.1.1. And again, to save it, we simply close that. Let's go to the final PC, PC2, which happens to be in a different subnet. And for sake of time, I'll paste the previous value in, and then I'll just change that 3rd octet. Now, I'll also enter that. Oops, did not enter that correctly. My bad. 192.168.2.1, and now let's press tab. Let's look at our numbers first. I just typed in for subnet B for PC2 192.168.2.31. Subnet mask is correct. My default gateway is the first usable address in that second subnet, which we're calling subnet B 192.168.2.0. I'll close this out. And at this point in time, we've pretty much configured everything except the interfaces on the routers. And you can see in our document on the left, those are the only values that are left to configure. So let me do that. We click on the router itself. Actually, you know what? We're not going to click on the router. We could. I'll show you. You could click on the router and click into CLI and then begin to configure, like type no, because we're going to do it manually. But I think it'd be a great learning opportunity to have to use the console cable. The way you get the console cable, remember, is to go to that lightning bolt icon, click on it, and then the blue console cable, the baby blue one, will be right here. We'll use PC1 to connect into the router. So let me left click the cable. We are going to use the RS-232 connection, register standard 232. The idea that this interface, in this case a COM port, is responsible for communicating serially using a certain bit rate. We'll see that in just a moment. Certain width, you name it. So I clicked on the PC1 with the console cable. Now I'll click on the router, and we have to connect into the console port. So now, in order to log into or connect into the router from the PC using the blue cable, let's click on PC1, and I'm going to click Terminal, this icon right here. Here's that bit rate I was talking to you about. It's also called the baud rate. Here's the data bits. What are we sending? If there's any parity used, in this case, these are the default values we want to leave. If I click OK, we'll be typing away. So let me scoop this up. And we're not going to change the router name, so we're just going to move right into privileged mode by typing enable. After that, we'll type in configure terminal to get into global configuration mode. And then last but not least, let me actually scoot this to the left so you can see, we're going to configure the FA0 interface first. So I'll type interface FA00. There are shortcuts to these commands, and we'll talk about them either in class or also in future demonstrations. By typing interface FA00, we are now in the proper configuration mode, which would allow us to make changes to this interface we see here. Now, if this were a GUI and we logged into a router, imagine it's an AdTran router, it's a brand that exists, you would simply be going into some left column navigational bar, and you'd be looking for interfaces, and then you'd click on interface FA00, and then there'd be some text fields that you could enter the proper IP address and also the mask, like we did with the PCs with the GUI portion. For our purpose, remember, we're using Cisco, we're using the command line, so we have to think about how we would do that from that perspective, that I have to type commands to get to the right levels to do the right things. It's no different if we want to start a program within Windows command prompt. We might navigate to the proper drive, see program files, if we're dealing with XP, jumping into then the proper folder, Mozilla, Firefox, and then the right executable. We really have to get to that right level or that right directory, you might say. And remember, we have to think about that too for Cisco command prompt programming or configurations. All right, so I'm going to type IP address 192.168.1.1, enter the proper mask, and I will also type no shutdown to turn the interface on. If you look to the left, you'll see that interface is now green. I'll leave those commands on the screen for the moment. The left subnet is operational now. The 192.168.1.0 subnet, it works. We're going to see to what extent in a moment, but everything works. I'm going to hit enter, and I'm going to type exit to move back a level. For those of you watching at home who've read up on Cisco, you didn't necessarily need to do that, but it's helpful to think about what level you're at. So in this case, we're going to scoot back a level, go back up to the global config mode. You can see that's labeled config. And then we'll configure the other interface, interface FA01, the interface that happens to be on the right side of the router. I'm going to use shortcuts to more expediently enter or configure our information. If I press up a couple times, I'm going to go back to the information that we typed just a moment ago. Now, the only difference is that third octet value. I'm showing you that I can work efficiently and accurately, carefully as well, to enter the right default gateway interface address for the interface Fast Ethernet 01. Press enter. Let me go back to the no shutdown. I don't need to type it. I can just toggle with the up arrow. That's what I've been doing. And turn that on as well. And if I look to the right, I notice that link now, that interface is green. And the link is almost established. This orange, or amber, it will turn to green shortly or soon enough. If I wanted to speed it up, I could just as easily click fast forward time to kind of speed up that discovery negotiation process that's happening behind the scenes to make sure that there is an electrical circuit that's established and that's properly functioning. All right, with that being said, I'm going to close this out. I'm also going to close out this window. We don't need that anymore. I'll actually minimize it for now. Let me double click on the top bar here. There we go. And so here is our diagram in full force. What we want to demonstrate is first what communication looks like when PC0 speaks to PC1. Now, in order to do that, we're going to click here on this tab behind the real-time tab, and I'll left-click, and this will bring me to simulation mode. With real-time tab, it simply allows you to test right there in the moment. What would happen if I pinged from 0 to 1? Did it work? Did it not work? Success, failure, that's it. We actually want to see this model and the test or this experiment play by play. We want to literally follow it frame by frame. Hey, what happens now? What message gets sent out? Where does the frame go? We want to be able to follow this one step at a time and not just query through all this and go 0 to 60 miles an hour in 5 seconds, or in this case, 5 milliseconds. We want to truly chronicle or observe what's going on. So we've switched to simulation mode. We'll stay there. The other thing I want to show you, if I click on PC0, I go to the command prompt. I'd like to type ARP-A. Yep. And I want to show you that in this computer's address table, there are no entries. This address table for ARPing is used to map or to link a computer's IP address to that particular computer's MAC address. So we're mapping a logical address to a physical address. So let me close that for now. And let's go over to our ping envelope. Remember, this is the normal ping envelope. It's not the one with the letter sticking out of it. This one would allow you to do some great customization testing. So I'll left click on that. I will ping from this PC to this PC. Now, what's supposed to happen with ping is you are essentially sending an echo request message, message type 8, from one computer, the source, to a destination, the recipient. And the whole purpose is to see if that other node exists. Ping really does derive itself from the sonar community. You heard me say it sends an echo request. It's no different than with sonar. Imagine submarines and you're using sonar, sound waves, to send a sound wave out and see, when it ultimately bounces back to us and kind of begin to judge, how close we are to something. Well, we could say ping's kind of doing that for us. We're kind of doing the knock, 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 are you there? I want to see if you're alive and operational. And so in this case, we're doing that. Now what I want you to see first is I pinged from the .11 device to the .21 device. So I'm going to click on this blue packet right here. I will left click and then it will open up what's going on behind the scenes. I could just as easily also click on the envelope here. I'll show you both as we look at this. But if I click on this blue square up in our simulation panel, you'll notice at layer 3, we know who we're sending it to, which is .21, and we know who we're sending it from, ourselves, .11. And we also know, let me click on here, we also know our own MAC address. We don't see that right now, but we do know our MAC address, but we don't know the destination MAC address. Again, we're trying to communicate to another computer in our subnet, and in order to do so, when we send out a packet, we have to fill in all the layers of communication. So in this case, with the ping packet, we're needing to fill in the information for layer 3, the network layer, and also layer 2. But we don't know that. We saw in our ARP table there were no entries. Consider it like a phone book of sorts. We don't have any contacts. And so we do need to reach out and find out that particular piece of information. So we'll have to kind of get to know this person. The way we do that, the way we find out what their MAC address is to stop with our ping. Notice we paused, and we move over to something called ARP, which is Address Resolution Protocol. The idea here is to send a broad sweeping message, in this case, to every possible node in our subnet, in our local area network, and really ask the question, who has the IP address .1.21, the person we're trying to learn, to figure out. And the way we do that, you can see right here at layer 2, again, this is our MAC address, source MAC address. The destination MAC address, FFFF, 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 the ultimate F-bomb. Well, this particular MAC address is called a broadcast MAC address. And if we think about this at the binary level, F in hex, if we convert that to binary, is 1111. So 4 bits where the bits are turned on to 1. And you then can realize, wow, there's 12 F, so 12 times 4 is 48. So there are 48 bits, and they're all turned on. They're all turned to 1. So this is the extreme, one polar extreme, where we say, look, this is the way we communicate to everybody in our particular subnet. And so what will happen, let me show you here again. Here is now the outbound PDU. What's going on at the different levels? Well, with Ethernet, I already told you, you've got that broadcast MAC address. This is our source MAC address. The question we're asking, it's an ARP question, is who has the target IP? And, hey, I don't know your MAC address. I'd like to meet you. Please send me your MAC address. I need to essentially get to know you on a one-on-one basis, or kind of a first-name basis. In this case, I need to know your MAC address. So let me close this out. And what's going to happen is if we send the ARP message, it's going to go to the switch. The switch will read that we're sending it to FFFFFFFFFFF, right? And the switch will go, oh, you're sending it to the broadcast MAC address. We will need to send it out to everybody else that's connected in our subnet. In this particular diagram, the switch will send it to that router interface and this PC interface. Let me click play, and you'll see that happen. Right now, we should see a split. One message will go to the router interface, the other to the PC. Let me pause right there. What you'll see is the PC receives it, and the router discards it. The router discards it because it knows, it raises its hand and goes, that's not for me. Forget that, I need to erase that. I'm not 1.21. So it will discard, but what's noticeable is this router will receive it and respond in kind with the proper ARP response. Hey, that's me, and here's my MAC address. It's great to meet you. Again, if we're using that analogy. So let's play. And so we could now pause here and click on the packet. I can click on it here, or I could also click on it here. I'm going to show you now this. It's nice to be able to click on the information as it's in process. We're sending from the source to now, notice, this is the destination MAC address. We're sending from our IP to destination IP. And if I click in, let me go to outbound, sorry, same thing here, doesn't matter, it's just going through a switch. Notice we have those fields, but notice our information is listed in the target MAC. Now it's also listed here in the source MAC, but the target MAC is where we're being sent to, and the target MAC is where we're sending it back to, and this is now going to tell them, hey, this is who I am. They're going to read this source MAC address field and go, oh, that's the person who belongs to the .21 address. So let's continue. We'll pause it just a moment. And here comes the ping response. We'll let it happen. We'll pause it at the switch. We'll stop right here. We started to ping. We didn't have enough information. We needed to do some reconnaissance, some nice social icebreaker, get to know you kind of song and dance, So in this case, we had to send an ARP message. The ARP message was sent to the switch sent it to the PC and the router. PC1 responded. What I want to show you here is if I go back into the command prompt and press up, in our address book, our nice phone book. My mother used to have a phone book. I think she still does. It's 2015. Most of us just have contacts on cell phones or email. Email, Outlook, you name it, whatever app you're using. But my mother has had a phone book, and she has kept important phone numbers and addresses for many a decade. And think of this like your phone book. In this case, your address book. Hey, it will keep track of the people you know in your local area network, in your subnet. Let me repeat that. This address book, which is called an ARP table, some refer to it as ARP cache. The idea that we're storing that certainly for a time, is listed here. And I know one person now in my neighborhood. You might say in my zip code. We've used that analogy before. I know the people in my subnet. I'm not going to break out into Mr. Rogers. Do you know the people in your neighborhood? Again, I'm dating myself. I'm certainly older. But keep in mind, hey, do I know the people in my neighborhood? In this case, do I know their IP address mapped, linked, or associated with their proper MAC address? Again, do I know the logical address connected to the physical address? And the reason being, every time we send information, we follow these network models. We've looked at the OSI model or the TCP/IP suite. When we do that, we realize we're following that rule, those set of standards and those protocols are involved, and we must put a destination and source MAC address for layer 2. We must put a destination and source IP address for layer 3. If we don't, the package does not send. And we know that to be true with the United States Postal Service. If we don't put a destination address, how the heck do we know who we're sending it to? And in this case, the same was true. Hey, we have a letter. We know some information. We know their IP address. We know we want to send it to them. But within this type of kind of infrastructure, we need the destination IP address and the destination MAC address. So in this case, now we've learned it. Let me close this. To make a long story short, let's let this thing play through. We're now sending our ping packet, echo request. Are you there? And PC1 will respond, hey, let me tell you, let me let you know that I am there. I'm going to stop it right here by clicking on, again, this play button. It acts as a play and pause button. If you didn't realize there's a toggle mechanism in the middle, I could speed up that process. I could slow it down. For right now, we're just going to keep it here. I'll speed it up later for the next test. But notice, we now have a successful ping test between PC 0 and 1. Again, it took some network discovery or, again, meeting a neighbor of ours in the subnet. But now it works. We have their information, their contact information. And if we ever want to send to them again, I'm going to now delete this. Watch this. Delete. I'm going to click real time. If I ever want to send to them again, I'm going to have instantaneous success. And if I were to go back to the simulation mode and I were to do that again, I'll show you both. Here, if I did the sim mode and I played this thing out, I'll speed it up now. It's just going to go down and back. We know the person we're sending to. So if I click on the envelope, hey, I know who I am. That's my source MAC. I know who you are, your destination MAC, as well as the proper IP addresses, source and destination IP addresses. Here's our echo request. And I'll hit play. Boom, boom, there's the down. And if I send it back, I will show you one thing. Hey, if you use ICMP, Internet Control Message Protocol, the idea we're going to use ping, which uses ICMP, that protocol. What you do want to recognize, let me show you here. See if I can find it. There you go. Down at the bottom with this ICMP message, we're using type 0, which happens to be called an echo reply or response. Now, we don't see it anywhere listed here. You'd have to click into one of these tabs to go, oh, the type is, hex 0. The other one happened to be message type 8. All right, so let's finish that out. And we'll hit pause. We are a success. Houston, we have liftoff. Let me delete that. So up to this point, we looked at a diagram in Notepad. We built the diagram in Packet Tracer. We tested what communication looks like in a local area network from one neighbor to another. Again, all in the same subnet. The next test that I want to show you, this next experiment, now does something different. The whole purpose now is to test from pinging from PC 0 to PC 2. And it's important to note from the get-go that we're actually traversing from one subnet to another. That's something we have to just recognize right away so we can begin to see the big picture and see what happens behind the scenes. Right, before I continue with this test, I'm going to go back to real-time mode, and I'm going to make a ping from this PC to the router. I'm not going to get into the nitty-gritty details of why I did that. What I really was trying to do was to make sure that this PC could communicate to the router, much like what we just did in the previous example, but I'm not going to rehash that out. And that way, if I were to go click into this and go to the command prompt and type an ARP, this PC now has the router's MAC address in its table, in its address book. Okay, so now let's break back into our proof or our test. The goal, let me delete that. The goal now is, to, as I said earlier, to ping from PC 0 to PC 2. And so let me click on here and click on PC 2 and make sure this is set up correctly. It is. I am trying to ping from PC 0 to PC 2. I've already said to you that according to the network models we follow, like TCP/IP suite, we must fill in the data for the proper layer 2 MAC addresses and layer 3 MAC addresses. The problem with this particular scenario is we know the IP addresses, where we're coming from and where we're going to. We actually know our MAC address, our source MAC address, but because we don't know the proper destination MAC address, we don't know what to use. Now in this case, let's pause, and I'd like to remind you and hopefully drive home the point, which is this. Every time your computer in your local area network, in your subnet, wants to communicate to someone outside of your network, to someone in another geographical location that's in a different subnet, you always must forward your traffic to the default router gateway interface. Let me repeat that. Every time that you want to communicate to someone that's outside your network, to someone that's in a different subnet, you must forward your frames within the local area network, so within that subnet, to the gateway interface. Now let's pause and think about that. You're trying to ping from PC 0 to PC 2. What I just told you was, in order to do that, we're actually not going to use the destination MAC address of PC 2 because they're in a different network. They're removed from us. We're actually simply going to forward our traffic, our message, within our own context, within this local area network. So we send it in our subnet, again, those are synonymous, to the router's gateway interface. The reason we do that, remember, is this gateway is a gateway to other networks. That's what's meant by that term gateway. It's the way out. It's the gate to get to other places. And in our case, within networking, those other places are other networks. Or, again, synonymously, other subnets. Again, if we're just using those terms loosely. But I want to get to other places, other zip codes, as we've said before. So if I want to get to those other networks, I always send my information to the go-to man. My middleman, you might say. I like to refer to routers sometimes as middlemen. They will accommodate, they will forward our traffic down on the line to the proper network that it needs to get to. The router is a smart device, a layer 3 device. It's doing a lot of thinking for us. We don't really have to think much. We just go, oh, our router's our middleman. It's our facilitator. Forward it to the router's MAC address. And, we can kind of do this with our hands and go, well, we're clean, we're good to go. The router will take care of me. Now, in this example, the router will take care of us and forward on the traffic to the proper destination. If we had other routers in between, if we were traversing the internet, well, just understand that that router would take care of business, pass it on to the next router. That next router would take care of business, pass it on to the next router, and we would go hop by hop until we would reach our destination network, and specifically our destination host. So let's think about this. The whole purpose when we want to ping someone outside our network is to send or move or forward our data to the default gateway's NIC, in this case the FA00 interface. I've already shown you we only had one entry in the ARP table, which was this PC. So what we end up doing right here, notice again, we're going to do another ARP. Hey, I need to meet people in my neighborhood. In this case, I need to meet the most important person in my neighborhood, the block captain, right? I need to meet that most important person because they're going to facilitate for me. They're going to forward my traffic on to the respective subnet. It's going to get the job done for me. So we again send it to everybody, the FFFF broadcast MAC address, which sends it to everybody in the subnet. And we're ultimately going to receive a response, say, hey, I got your message. I'm the person you're looking for. Here are my credentials. Here's my information. Now, one thing to point out, since we've talked about broadcast MAC addresses, is when we send it to the switch, remember the switch knows that since it's that FFFF, right, that F-bomb, since it knows it's supposed to send to everybody, remember it's only sending to everybody who's connected. So if we look on here, there are only 3 interfaces we've connected to, FA01, FA03, FA02. Well, it doesn't send to the interface it came in on, so again, we'll forward it, I'll show you. we're only forwarding it, right here, pause, it came in on FA01, so we're going to forward it out to FA03 and FA02, to all other connected interfaces. It never sends it to FA04 or 05 because there's no electrical circuit to continue that electrical current on. So we'll run this through. We know that the PC is going to say, no, that's not me. The router responds, yes, that's me. And now the PC can send a proper ping to the router. The router can respond and push it on to PC2. Now PC2 can respond back to router, who acts as this intermediate relay agent, a routing device, routing between subnets. Let me click pause, quick catch of that. And now we had a complete ping. I'm PC0. I did not know my default router before I pinged my PC2 counterpart in the other subnet. But now I do. How do I know that? Because I did an ARP request. I did this ARP message that's sent to everybody in my subnet, so I got to know that person I wanted to meet, in this case the default router's interface, FA00. Since I got to meet them, I put them in my address book. Let me press up. I'll show you. I've got 2 addresses now. Voila! I have met 2 people in my subnet, in my particular network, the 192.168.1.0 network, and now I know a little bit more about my surroundings. I know more people. Now, if you're wondering, since we've done this, we're going to stop here. We're just going to hash out a few more things and wrap up the demo. Every time, so we turn our computer on, the ARP table's empty. Every time we want to send to someone in our network, and we've never met them before, we must go through that song and dance. And again, this is all specific to IPv4. It's different than IPv6. So keep that in mind. This is a tried and true concept for IPv4. This is the way it works. This is what happens behind the scenes. I've got to meet the people in my network, in my subnet, 192.168.1.0, in that network. And I have to meet them, and I have to learn their MAC addresses, their physical addresses, before I can truly package the frame to be able to send it to them, to be able to converse with them. So I know we've only got 3 nodes connected, in this case, to that network. Well, imagine we're in a larger corporate enterprise setting, and we have 500 computers that are all connected to switches that are essentially daisy-chained together to kind of create a unified switch. It's something you can do. So you could have many 48-port switches that are just linked together to create one master switch, a mega switch perhaps, with all these ports. Well, if we're all on that same subnet and all 500 nodes are connected to it, every time we meet someone and we send that broadcast MAC address in the form of the ARP message, the ARP broadcast, we send it to the switch has to disseminate that or send it out, broadcast it out to all other 499 people who are waiting, standing by. Now, remember, we're only trying to reach one person out of the remaining 499. So the 498 people get the message and go, that's not for me. Let me discard that. The one obvious negative in this is for that split second, or we probably would say for those milliseconds, we certainly have used a little bit of bandwidth to try and take part in this learning discovery process to meet one of our neighbors in our subnet, in our zip code, if you will. So that's something that happens. As you get further along within IPv4 and networking, you'll realize DHCP also will broadcast. If we're a client user and we're trying to find a particular DHCP server on our network, we're going to have to do that too. Hey, are you out there? Is our DHCP server? So there are moments in the day of a network where there are moments of heavy bandwidth utilization, where we actually have to send a broadcast message. It sends it to many people. Yeah, really, there's only one intended recipient, but in order to kind of reach everybody, because we don't know about other people on our network, we have to do it anyway. So keep that in mind. With that being said, we will wrap up this particular demo discussion. Remember, if there's any more questions, check out your book, email me, connect with me in class or during lab. You have many avenues to reach out and ask for help or brainstorm further with me. All right, take care. Have a great week.